The universe exists in direct violation of the fundamental laws of physics. This statement represents one of the most profound paradoxes confronting modern cosmology, yet it forms the foundation of our reality. According to our most sophisticated theoretical models and experimental observations, the cosmos should have annihilated itself within the first fraction of a second following the Big Bang, leaving behind nothing but empty space and radiation. 13.8 billion years ago, the Big Bang created equal quantities of matter and antimatter in a cosmic furnace of unimaginable energy density. These two forms of substance possess identical masses but opposite electrical charges, creating a perfect symmetry that should have resulted in complete mutual destruction. When matter encounters antimatter, both particles convert entirely into pure energy, typically manifesting as high-energy gamma radiation. This process, known as annihilation, represents one of the most efficient energy conversion mechanisms known to physics. The mathematical precision of this relationship demands that every electron should have been matched with a positron, every proton with an antiproton, and every neutron with an antineutron. The inevitable collision between these particle pairs should have transformed the entire universe's mass into electromagnetic radiation within microseconds of creation. The cosmos we observe today, filled with galaxies, stars, planets, and conscious beings capable of contemplating their own existence, should never have formed. Yet we exist within a universe composed almost entirely of matter, with antimatter appearing only as fleeting traces in high-energy cosmic ray interactions and particle accelerator experiments. The European Organization for Nuclear Research, commonly known as CERN, has quantified this asymmetry with remarkable precision. For every billion matter-antimatter pairs that annihilated in the primordial universe, exactly one additional matter particle survived the cosmic holocaust. This infinitesimal imbalance of 1 part in a billion represents the sole reason for the existence of everything we observe. The magnitude of this mystery extends beyond mere academic curiosity. The matter-antimatter asymmetry problem challenges our fundamental understanding of symmetry in nature, forces us to question the completeness of our theoretical frameworks, and suggests the existence of physical processes that remain hidden from our current experimental capabilities. The resolution of this paradox may require revolutionary advances in particle physics, potentially revealing new fundamental forces or exotic particles that operated exclusively during the universe's first moments. Scientists worldwide have dedicated decades to unraveling this cosmic enigma, constructing increasingly powerful particle accelerators and developing sophisticated theoretical models to explain how the universe escaped its predicted fate. The implications of solving this mystery extend far beyond academic achievement, potentially unlocking the secrets of cosmic evolution, the nature of space and time, and the ultimate question of why something exists rather than nothing. The journey to understand this asymmetry leads us through the most extreme conditions imaginable, where temperatures exceeded trillions of degrees and densities approached those found within atomic nuclei. In these primordial moments, the laws of physics operated under circumstances so extreme that our current theories reach their limits of applicability. The answer to why the universe exists may lie hidden within these first microseconds, waiting to be discovered through the combined efforts of theoretical physics and experimental investigation. This documentary examines humanity's quest to solve the greatest existential puzzle in science, exploring how a microscopic imbalance in the fundamental properties of matter and antimatter allowed complexity, structure, and ultimately consciousness to emerge from the cosmic void. The Big Bang represents the most violent and consequential event in cosmic history. 13.8 billion years ago, the entire observable universe emerged from a singularity smaller than a subatomic particle, expanding faster than the speed of light in a process physicists term cosmic inflation. Within the first trillionth of a trillionth of a trillionth of a second, space itself stretched by a factor exceeding 10 to the 26th power, creating the fundamental framework within which all subsequent cosmic evolution would unfold. During these initial moments, temperatures reached values incomprehensible to human experience. The cosmic furnace burned at 10 to the 32nd degrees Kelvin, approximately 10 billion times hotter than the core of our Sun. Under these extreme conditions, the distinction between matter and energy became meaningless as particles spontaneously created and destroyed themselves in accordance with Einstein's mass-energy equivalence principle. The fundamental symmetries governing particle physics demanded that this primordial cauldron produce equal quantities of matter and antimatter. Every electron that materialized from the quantum vacuum required the simultaneous creation of its antimatter counterpart, the positron. Each proton emerging from the energy density fluctuations necessitated the formation of an antiproton possessing identical mass but opposite electrical charge. The laws of physics, as we understand them today, permit no alternative outcome. This symmetrical creation process represents more than theoretical elegance. Conservation laws, which form the bedrock of modern physics, mandate that certain properties remain constant throughout all physical interactions. The conservation of electric charge requires that the total electrical charge of the universe must equal zero, demanding that every positively charged particle be balanced by a corresponding negative charge. The creation of matter particles without their antimatter counterparts would violate these fundamental principles, effectively rewriting the laws governing reality itself. Matter constitutes the substance of everything we observe in the universe. Every atom composing your body, every molecule of air you breathe, and every distant galaxy visible through our most powerful telescopes consists of matter particles. At the most fundamental level, ordinary matter derives from three basic building blocks: electrons, protons, and neutrons. Electrons carry a negative electrical charge and orbit atomic nuclei, while protons possess positive charges and reside within the nucleus alongside electrically neutral neutrons. Antimatter represents the perfect mirror image of ordinary matter. For every matter particle that exists, nature has created a corresponding antiparticle possessing identical mass but opposite electrical properties. The positron, discovered in 1932 by physicist Carl Anderson, carries the same mass as an electron but bears a positive rather than negative charge. Antiprotons mirror protons in every respect except their negative electrical charge, while antineutrons, despite having no net electrical charge like ordinary neutrons, possess opposite magnetic properties. The concept extends beyond simple charge reversal. Antimatter particles exhibit opposite values for all quantum numbers, including properties such as baryon number, lepton number, and various exotic quantum characteristics that govern particle interactions. These quantum numbers serve as fundamental identifiers, distinguishing different particle species and governing their behavior under the four fundamental forces of nature. Modern particle accelerators routinely create antimatter particles through high-energy collisions. When protons collide at sufficient energies, the impact generates particle-antiparticle pairs, according to Einstein's famous equation E equals mc squared. These antimatter particles exist only briefly in our matter-dominated environment before encountering their matter counterparts and undergoing annihilation. The annihilation process between matter and antimatter represents the most efficient energy conversion mechanism known to physics. When an electron encounters a positron, both particles disappear completely, converting their entire rest mass into electromagnetic radiation, according to Einstein's mass-energy relationship. This process transforms matter into pure energy with 100% efficiency, far exceeding the fusion reactions powering stars or the most advanced nuclear technologies developed by human civilization. The energy release from matter-antimatter annihilation follows precise mathematical relationships. A single gram of antimatter colliding with a gram of ordinary matter would release energy equivalent to 43 million tons of TNT, approximately 3 times the explosive yield of the most powerful nuclear weapons ever detonated. This tremendous energy density explains why antimatter represents both a theoretical curiosity and a potential future technology for spacecraft propulsion and energy generation. In the primordial universe, with equal amounts of matter and antimatter in intimate contact, complete annihilation should have proceeded inevitably. The extremely high particle densities and temperatures of the early cosmos ensured frequent collisions between particles and their antiparticle counterparts. Every electron should have found a positron, every proton should have encountered an antiproton, and the resulting gamma-ray radiation should have filled an otherwise empty universe. The mathematical certainty of this outcome makes our existence profoundly puzzling. The universe we observe contains approximately 10 to the 80th atoms, organized into roughly 2 trillion galaxies, each containing hundreds of billions of stars. The cosmic microwave background radiation, the afterglow of the Big Bang, provides no evidence for the massive gamma-ray flux that should have resulted from universal matter-antimatter annihilation. Instead, we find a cosmos dominated by matter, with antimatter appearing only as brief flashes in cosmic ray interactions and particle physics experiments. The matter-antimatter asymmetry problem ranks among the most profound mysteries confronting modern physics. The European Organization for Nuclear Research has determined that the current universe contains approximately 1 matter particle for every 10 billion photons in the cosmic microwave background. This ratio implies that during the first moments following the Big Bang, for every billion matter-antimatter pairs that annihilated into radiation, exactly 1 additional matter particle survived the cosmic holocaust. This infinitesimal asymmetry of 1 part in a billion appears almost negligible, yet it represents the difference between existence and non-existence for everything we observe. Without this tiny imbalance, the universe would contain only electromagnetic radiation propagating through empty space. No atoms could form, no chemical elements could exist, and no complex structures capable of supporting life could ever emerge. The precision required for this asymmetry suggests underlying physical processes of extraordinary subtlety. The mechanisms responsible for generating this imbalance must have operated with exquisite accuracy during the universe's first microseconds, when temperatures and energy densities exceeded anything achievable in terrestrial laboratories. The standard model of particle physics, despite its remarkable success in describing fundamental particles and their interactions, provides insufficient explanation for this observed asymmetry. The resolution of this mystery may require revolutionary advances in our understanding of fundamental physics. Scientists propose various theoretical frameworks, including modifications to the standard model, the existence of undiscovered particles, or entirely new physical principles governing the behavior of matter and antimatter during the universe's earliest moments. The answer to why matter dominates antimatter could unlock secrets about the nature of time, the structure of space, and the ultimate fate of the cosmos. This question drives research at the world's most sophisticated particle physics facilities, where scientists recreate conditions similar to those existing moments after the Big Bang. The Large Hadron Collider at CERN, along with other advanced experimental apparatus worldwide, continues probing the fundamental asymmetries between matter and antimatter, seeking clues that might explain why anything exists at all. The implications extend far beyond academic curiosity. Understanding the origin of matter-antimatter asymmetry could reveal new physics beyond our current theoretical frameworks, potentially leading to technological applications we cannot currently imagine. More fundamentally, solving this puzzle addresses the deepest existential question science can pose. Why does the universe contain something rather than nothing? Every atom constituting your body, every star illuminating the cosmos, and every galaxy spanning billions of light years consists of matter particles that possess specific measurable properties. The electron carries a negative electrical charge of -1 elementary charge unit, while the proton maintains a positive charge of exactly +1. These fundamental particles combine to form the atomic structures that comprise all observable reality. Antimatter represents the precise mirror image of ordinary matter, exhibiting identical mass but opposite electrical charge. The positron, antimatter's counterpart to the electron, carries a positive charge of +1 elementary charge unit while maintaining the exact same mass as its matter equivalent. Similarly, the antiproton possesses a negative electrical charge but retains the proton's mass of approximately 938 million electron volts. The symmetry extends beyond simple charge reversal. Antimatter particles exhibit opposite magnetic moments, reversed quantum spin orientations, and inverted parity states compared to their matter counterparts. This mathematical precision in opposition creates what physicists term charge parity conjugation symmetry, suggesting that the fundamental laws of physics should treat matter and antimatter as equivalent phenomena operating under reversed conditions. Antimatter production occurs naturally in high-energy cosmic processes, including stellar nucleosynthesis, radioactive decay, and cosmic ray interactions with atmospheric particles. Particle accelerators routinely generate antimatter through high-energy collisions, though the quantities produced remain microscopic. CERN's antimatter factory produces approximately 10 billion antiprotons annually, yet this represents merely 10 nanograms of material, insufficient to power a light bulb for more than a few seconds. The encounter between matter and antimatter triggers the most efficient energy conversion process known to physics. When a particle contacts its antiparticle counterpart, both entities undergo complete mass-to-energy conversion according to Einstein's mass-energy equivalence relationship, E equals mc squared. This transformation achieves 100% efficiency, converting the entire rest mass of both particles into electromagnetic radiation. Electron-positron annihilation typically produces 2 gamma-ray photons, each carrying energy equal to the electron's rest mass of 0.511 million electron volts. The photons emerge in precisely opposite directions to conserve momentum, traveling at light speed through space until they interact with matter. Proton-antiproton annihilation releases significantly more energy, approximately 1.876 billion electron volts, often manifesting as multiple high-energy particles including pions, kaons, and additional gamma rays. The annihilation cross-section, which measures the probability of matter-antimatter collision, depends on the relative velocities and quantum states of the interacting particles. Low-energy encounters produce the highest annihilation rates, as particles spend more time in proximity, increasing interaction probability. This inverse relationship between energy and annihilation efficiency explains why antimatter storage requires sophisticated magnetic containment systems operating at temperatures approaching absolute zero. The energy release from matter-antimatter annihilation exceeds that of nuclear fusion by factors exceeding 100. 1 kilogram of antimatter annihilating with 1 kilogram of matter would release energy equivalent to approximately 43 megatons of TNT, highlighting both the tremendous potential and inherent danger of antimatter manipulation. Current antimatter production costs exceed $60 trillion per gram, making it the most expensive substance ever created. Astronomical observations reveal a universe composed almost entirely of matter, with antimatter appearing only as transient traces in high-energy environments. Ground-based gamma-ray telescopes detect no significant antimatter-matter boundary regions that would produce characteristic 511 kilo-electron-volt emission lines from electron-positron annihilation. Space-based observatories, including the Alpha Magnetic Spectrometer aboard the International Space Station, have measured cosmic ray antimatter ratios of approximately 1 antiproton per 10,000 protons. The absence of primordial antimatter regions eliminates several theoretical possibilities for explaining the observed asymmetry. If large antimatter domains existed within the observable universe, the boundaries between matter and antimatter regions would generate intense gamma-ray emissions detectable by current instrumentation. The lack of such signatures confirms that antimatter exists only in trace quantities produced by high-energy processes rather than primordial remnants. Cosmic microwave background radiation analysis provides additional evidence for matter dominance. The temperature fluctuations and polarization patterns observed by precision instruments such as the Planck satellite reflect density variations in ordinary matter during the era of recombination, approximately 380,000 years after the Big Bang. These measurements show no signatures consistent with significant antimatter presence during this critical epoch when atoms first formed. The quantified asymmetry reveals extraordinary precision in the fundamental imbalance. Current measurements indicate that for every billion matter-antimatter pairs created during the Big Bang, exactly one additional matter particle survived the annihilation process. This ratio of 1 part in 10 to the 9th power represents the sole source of all observable structure in the universe, from the smallest asteroids to the largest galactic superclusters. Paul Dirac's 1928 relativistic wave equation for electrons predicted the existence of antimatter through pure mathematical necessity. The Dirac equation required solutions with both positive and negative energy states, leading Dirac to propose that negative energy electrons represented a new form of matter with opposite charge. This theoretical prediction emerged from the intersection of quantum mechanics and special relativity, demonstrating the predictive power of fundamental physics. Carl Anderson's cosmic ray research at the California Institute of Technology provided experimental confirmation of Dirac's prediction. Using a cloud chamber placed within a magnetic field, Anderson photographed particle tracks produced by cosmic ray interactions with atmospheric nuclei. On August 2, 1932, he captured an image showing a particle with the same mass as an electron but opposite curvature in the magnetic field, indicating positive electrical charge. The discovery photograph revealed a particle track bending in the magnetic field with curvature radius, indicating a mass identical to the electron. The direction of curvature, however, demonstrated positive rather than negative charge, confirming the existence of the positron. Anderson's measurement precision eliminated alternative explanations such as protons or other known particles, establishing antimatter's reality through direct experimental observation. Anderson received the Nobel Prize in Physics in 1936 for this groundbreaking discovery, which opened entirely new research fields in particle physics and cosmology. The positron's existence validated quantum field theory's most radical predictions and suggested that every particle might possess an antiparticle counterpart. This discovery initiated the systematic search for additional antimatter particles, leading to the eventual detection of antiprotons, antineutrons, and complete antimatter atoms. The confirmation of antimatter's existence transformed our understanding of symmetry in nature and raised profound questions about the universe's composition. If physics demands equal creation of matter and antimatter, why does the observable cosmos consist almost entirely of ordinary matter? This question continues to drive experimental research and theoretical development in fundamental physics, representing one of the most significant unsolved problems in modern science. The Standard Model of particle physics represents humanity's most successful attempt to describe the fundamental components of reality. This theoretical framework encompasses 12 elementary particles and 3 of the 4 known forces, providing predictions that align with experimental observations to extraordinary precision. Yet this magnificent construction contains a fatal flaw that threatens its completeness. The Standard Model predicts that the universe should contain equal quantities of matter and antimatter, a conclusion that contradicts our existence. This inadequacy forces physicists to confront an uncomfortable truth. Our most comprehensive theory cannot explain why we are here to contemplate it. The model's inability to account for the observed matter-antimatter asymmetry indicates that crucial physics remains undiscovered, hidden within energy scales and conditions that current experiments cannot access. Within the Standard Model's mathematical structure, every matter particle possesses a corresponding antimatter counterpart with identical mass but opposite charge. The theory's fundamental symmetries demand that any process creating matter must simultaneously produce an equivalent amount of antimatter. This requirement emerges from the conservation laws that govern particle interactions, mathematical principles so fundamental that their violation would undermine the theoretical foundation of modern physics. The European Organization for Nuclear Research has repeatedly confirmed these predictions through decades of experimentation. When particles collide at high energies within the Large Hadron Collider, matter and antimatter emerge in precisely equal quantities, exactly as the Standard Model predicts. These observations validate the theory's accuracy, while simultaneously highlighting its inadequacy to explain cosmic evolution. The Standard Model's symmetries extend beyond simple charge conservation. The theory incorporates 3 discrete symmetries that should preserve the balance between matter and antimatter throughout cosmic history. Charge conjugation symmetry requires that physics remain unchanged when all particles transform into their antiparticles. Parity symmetry demands that physical laws appear identical when viewed in a mirror. Time reversal symmetry insists that fundamental processes work equally well when time flows backward. These symmetries combine to form the CPT theorem, one of the most rigorously tested principles in physics. The theorem states that any violation of one symmetry must be compensated by violations of the others, maintaining an overall balance that preserves the matter-antimatter equilibrium. The Standard Model respects this theorem completely, yet the universe clearly violates it on the largest scales. Baryogenesis represents the theoretical framework describing how the universe generated its observed excess of matter over antimatter. The term combines baryon, referring to particles like protons and neutrons that constitute atomic nuclei, with genesis, indicating creation. This process must have occurred during the universe's earliest moments, when conditions permitted violations of the Standard Model's restrictive symmetries. The concept requires that some unknown mechanism operating in the primordial universe preferentially created matter particles while suppressing antimatter production. This asymmetric process contradicts our current understanding of particle physics, suggesting that additional forces or particles influenced cosmic evolution during its first microseconds. The magnitude of this effect appears minuscule, producing only one extra matter particle for every billion matter-antimatter pairs, yet this infinitesimal imbalance determined the universe's ultimate fate. Baryogenesis must have operated under extreme conditions that no longer exist in the contemporary cosmos. The universe's initial temperature exceeded 10 billion degrees Kelvin, creating energy densities that approached those found within atomic nuclei. Under these circumstances, particles moved at relativistic speeds and interacted through processes that remain beyond our experimental reach. The physics governing these interactions may differ fundamentally from the Standard Model's predictions. The timing of baryogenesis remains critically important for understanding cosmic evolution. If the process occurred too early, subsequent interactions would have erased the generated asymmetry. If it happened too late, the universe would have cooled below the threshold required for matter-antimatter creation. The mechanism must have operated within a precise temporal window, possibly lasting only microseconds, during which the cosmos possessed exactly the right conditions for asymmetric particle production. Soviet physicist Andrei Sakharov identified three necessary conditions that any successful baryogenesis mechanism must satisfy. His 1967 analysis established the theoretical requirements for generating matter-antimatter asymmetry within a universe governed by fundamental physical laws. These conditions provide the framework for evaluating proposed solutions to the cosmic asymmetry problem, setting stringent criteria that any viable theory must meet. The first condition demands baryon number violation, requiring processes that change the total number of baryons in the universe. Under normal circumstances, particle interactions conserve baryon number absolutely, ensuring that protons and neutrons can neither be created nor destroyed without corresponding antiparticle production. Baryogenesis requires mechanisms that violate this conservation law, allowing the universe to generate a net excess of matter particles. Such processes must involve physics beyond the Standard Model, potentially through interactions mediated by unknown particles or forces. Experimental searches for baryon number violation have focused primarily on proton decay, a process that would demonstrate the instability of matter's fundamental constituents. Despite decades of increasingly sensitive measurements, no experiment has observed a single proton decay event. These null results establish lower limits on proton lifetime that exceed 10 to the 34th years, far exceeding the universe's current age. The absence of detectable proton decay suggests that baryon number violation, if it occurs, operates through mechanisms more subtle than simple particle decay. The second condition requires C and CP violation, mandating that the laws of physics distinguish between matter and antimatter. C violation, or charge conjugation violation, means that processes involving particles differ from identical processes involving antiparticles. CP violation combines charge conjugation with parity transformation, requiring that nature distinguishes between left-handed and right-handed versions of particle interactions. These violations must be sufficiently large to generate the observed cosmic asymmetry, yet small enough to remain consistent with laboratory measurements. Experimental evidence for CP violation first emerged in 1964 through studies of neutral kaon decay, earning James Cronin and Val Fitch the Nobel Prize in Physics. Subsequent experiments have confirmed CP violation in several particle systems, including B mesons and, more recently, D mesons. However, the magnitude of observed CP violation falls short of explaining the cosmic matter-antimatter asymmetry by several orders of magnitude. Additional sources of CP violation, beyond those predicted by the standard model, appear necessary to account for the universe's composition. The third condition demands thermal disequilibrium, requiring that baryogenesis occurred during periods when the universe's expansion prevented particle interactions from reaching equilibrium. Under equilibrium conditions, forward and reverse reaction rates balance precisely, preventing any net change in particle populations. The universe's rapid expansion during its earliest moments created conditions where reaction rates could not keep pace with cosmological cooling, allowing asymmetric processes to operate effectively. The expansion rate during the relevant epoch exceeded the interaction rates of particles responsible for maintaining matter-antimatter balance. This circumstance created a cosmological environment where asymmetric processes could produce lasting effects rather than being immediately erased by equilibrium reactions. The precise timing of this disequilibrium determines when baryogenesis could operate most effectively, establishing temporal constraints on viable theoretical mechanisms. These three conditions must operate simultaneously to produce the observed cosmic asymmetry. The interplay between baryon number violation, CP violation, and thermal disequilibrium creates a narrow window of opportunity during which the universe could generate its matter excess. Understanding how these requirements combine in realistic cosmological scenarios represents one of the primary challenges facing theoretical physicists working to solve the asymmetry problem. The search for mechanisms satisfying Sakharov's conditions has motivated extensive theoretical research and experimental investigation. Scientists have proposed numerous baryogenesis scenarios, each attempting to identify specific processes that could operate under early universe conditions while satisfying these fundamental requirements. The resolution of this cosmic mystery awaits the discovery of new physics that extends beyond our current theoretical understanding. The pursuit of understanding matter-antimatter asymmetry requires recreating the conditions that existed in the first moments after the Big Bang. This endeavor demands machines of extraordinary power and precision, capable of accelerating particles to velocities approaching the speed of light and generating collision energies that mirror the primordial universe. These technological marvels represent humanity's most ambitious attempt to probe the fundamental nature of reality itself. Beneath the Franco-Swiss border, 27 kilometers of superconducting magnets form the most powerful particle accelerator ever constructed by human civilization. The Large Hadron Collider operates at temperatures colder than the vacuum of space, maintaining its superconducting state through liquid helium cooling systems that achieve temperatures of -271 degrees Celsius. This engineering achievement enables magnetic fields with strengths exceeding those found at the surface of neutron stars. The machine accelerates protons through its circular tunnel in opposite directions, reaching energies of 6.5 tera-electronvolts per beam. When these particle streams collide at designated interaction points, they generate temperatures exceeding 100,000 times the core temperature of the Sun. These conditions replicate the energy densities that existed when the universe was less than 1/1,000,000th of a second old, providing scientists with a laboratory-scale recreation of cosmic genesis. The collision process transforms kinetic energy into mass according to Einstein's mass-energy equivalence principle, spontaneously creating exotic particles that existed only in the primordial universe. These newly formed particles exist for infinitesimal fractions of a second before decaying into more stable forms, leaving behind traces that sophisticated detection systems analyze to reconstruct the original collision events. Each second, the Large Hadron Collider produces approximately 1 billion proton-proton collisions, generating data at rates that challenge the limits of modern computing infrastructure. The machine's construction required unprecedented international cooperation, involving contributions from over 100 countries and representing an investment exceeding $10 billion. The engineering challenges included developing superconducting magnets capable of maintaining precise magnetic fields across vast distances, creating ultra-high vacuum conditions throughout the accelerator ring, and constructing detection systems sensitive enough to track individual subatomic particles traveling at near-light speeds. The Large Hadron Collider Beauty Experiment, designated LHCb, occupies a unique position among the facility's 4 major detection systems. While other experiments focus on discovering new particles or studying the Higgs mechanism, LHCb specializes exclusively in investigating the subtle differences between matter and antimatter behavior. The detector spans 21 meters in length and operates with measurement precision that exceeds 1 part in 10 billion, enabling scientists to detect asymmetries so minute they would otherwise remain invisible. The experiment concentrates on particles containing bottom quarks, known as B mesons, which provide an ideal laboratory for studying charge parity violation. These particles possess the remarkable property of oscillating between matter and antimatter states approximately 3 trillion times per second, creating opportunities to measure behavioral differences with unprecedented sensitivity. The LHCb detector tracks these particles' decay patterns, recording the precise trajectories and energies of their decay products to identify violations of fundamental symmetries. The ATLAS experiment operates as a general-purpose detector designed to investigate the broadest possible range of physics phenomena. Its cylindrical structure measures 46 meters in length and 25 meters in height, making it the largest volume particle detector ever constructed. A TLAS contributed to the discovery of the Higgs boson and continues to search for evidence of supersymmetric particles and extra dimensions that could explain the matter-antimatter asymmetry. The Compact Muon Solenoid Experiment, known as CMS, provides complementary measurements to ATLAS through its distinctive design featuring the world's largest superconducting magnet. The detector's magnetic field strength reaches 3.8 Tesla, approximately 100,000 times stronger than Earth's magnetic field, enabling precise momentum measurements of charged particles. CMS has produced groundbreaking studies of CP violation in various particle systems and continues to probe the limits of the standard model. These experiments generate data at unprecedented rates, with each detector recording information from millions of particle collisions every second. The computational challenge of analyzing this information requires distributed computing networks spanning the globe, processing petabytes of data annually. The analysis process involves sophisticated statistical techniques to extract signals of new physics from overwhelming backgrounds of known processes. The quest to understand matter-antimatter asymmetry extends far beyond CERN's facilities, encompassing research institutions across every continent. Fermi National Accelerator Laboratory in the United States operates complementary experiments that investigate different aspects of the asymmetry problem through alternative experimental approaches. The laboratory's main injector neutrino oscillation search experiment studies how neutrinos change between different types during their journey through matter, potentially revealing new sources of CP violation. The High Energy Accelerator Research Organization in Japan, commonly known as KEK, houses the Belle 2 experiment, which studies B meson decays with extraordinary precision. This facility utilizes electron-positron collisions to create B mesons under controlled conditions, providing measurements that complement and verify results obtained at the Large Hadron Collider. The Japanese approach enables studies of rare decay processes that occur in fewer than one collision per billion, requiring years of data collection to achieve statistical significance. The Deep Underground Neutrino experiment, currently under construction between Fermilab and South Dakota, will investigate whether neutrinos and antineutrinos exhibit different oscillation patterns during their 800-kilometer underground journey. This experiment could reveal fundamental asymmetries in the neutrino sector that contribute to the universe's matter dominance. The detection systems, housed in caverns excavated 1.5 kilometers underground, will contain 40,000 tons of liquid argon maintained at temperatures of minus 184 degrees Celsius. International collaboration extends beyond individual experiments to encompass theoretical research programs that interpret experimental results and predict new phenomena. The worldwide community of particle physicists maintains constant communication through conferences, workshops, and collaborative research projects that ensure rapid dissemination of discoveries and coordinate future experimental priorities. The financial investment in these global efforts reflects humanity's commitment to understanding fundamental questions about existence itself. Annual expenditures exceed several $1 billion, supporting thousands of scientists, engineers, and technicians dedicated to unraveling the universe's deepest mysteries. The technological innovations required for these experiments frequently find applications in medical imaging, materials, science, and computational methods that benefit society far beyond particle physics research. These interconnected efforts represent the culmination of human scientific achievement, combining theoretical insight with engineering excellence to probe the most fundamental questions about reality. The collaboration transcends national boundaries, political differences, and cultural divisions in pursuit of knowledge that belongs to all humanity. The results emerging from these experiments are beginning to provide the first concrete clues about why the universe chose existence over annihilation, setting the stage for discoveries that may revolutionize our understanding of cosmic evolution. The year 2020 marked a watershed moment in particle physics when researchers at the Large Hadron Collider beauty experiment achieved what many considered impossible: the direct observation of a previously unknown form of matter-antimatter asymmetry. This breakthrough emerged from years of meticulous data collection and analysis, challenging the very foundations of our understanding about the universe's fundamental structure. The Large Hadron Collider beauty experiment represents one of the most sophisticated scientific instruments ever constructed, specifically engineered to investigate the subtle differences between matter and antimatter through the study of particles containing bottom quarks. These particles, known as B mesons, possess unique properties that make them ideal laboratories for examining charge parity violation, the phenomenon responsible for the universe's matter dominance. The LHCb detector stretches across 45 meters of underground cavern at CERN, equipped with tracking systems capable of measuring particle trajectories with unprecedented precision. The experiment operates by accelerating protons to 99.9% the speed of light before colliding them head-on, recreating conditions similar to those present microseconds after the Big Bang. Within these high-energy collisions, B mesons form and decay within trillionths of a second. their brief existence providing crucial insights into the fundamental asymmetries governing particle interactions. The experimental design focuses specifically on forward-angle particle production, where the most significant asymmetries between matter and antimatter manifestations occur. Advanced silicon detectors record the paths of charged particles with micrometer accuracy, while electromagnetic calorimeters measure the energy deposits from photons and electrons. This combination of detection systems allows researchers to reconstruct the complete decay sequences of B mesons, identifying subtle differences in how matter and antimatter versions of these particles behave. The collaboration involves over 1,000 physicists from 18 countries, each contributing specialized expertise in detector technology, data analysis, and theoretical interpretation. The scale of data processing required for this research exceeds the computational capabilities of individual institutions, necessitating distributed computing networks that analyze petabytes of collision data annually. The statistical precision demanded by these measurements requires the accumulation of billions of B meson decays, a process that has continued for over a decade of continuous operation. The discovery that emerged from this massive experimental effort centered on a specific type of B meson known as B sub 0, a particle composed of a bottom quark bound to a strange antiquark. These particles exhibit a remarkable quantum mechanical phenomenon called oscillation, spontaneously transforming between matter and antimatter states approximately 3 trillion times per second. This rapid oscillation creates opportunities to observe fundamental asymmetries that remain hidden in more stable particles. The LHCb team discovered that B sub-0 mesons and their antimatter counterparts do not decay at identical rates, revealing a violation of charge parity symmetry that exceeded all previous theoretical predictions. The asymmetry manifested in the decay pathways these particles follow when they transform into lighter particles, with matter versions showing statistically different behavior compared to their antimatter equivalents. This observation required the analysis of over 6 billion B meson decays accumulated over 8 years of data collection. The statistical significance of this discovery reached what physicists term 5 sigma, meaning the probability of observing such an effect by random chance is less than 1 in 3.5 million. This level of confidence represents the gold standard for particle physics discoveries, comparable to the statistical certainty achieved for the Higgs boson detection. The measurement revealed an asymmetry parameter of negative 0.008 plus or minus 0.003, indicating that antimatter B sub S0 mesons decay approximately 0.8% more frequently than their matter counterparts. The precision required to measure this minute difference pushed experimental techniques to their absolute limits. The researchers had to account for systematic uncertainties arising from detector efficiency variations, background contamination from other particle processes, and subtle biases in data reconstruction algorithms. Advanced statistical methods, including machine learning techniques, were employed to separate genuine asymmetry signals from experimental artifacts that could mimic the expected signature. The implications of this discovery extend far beyond the specific behavior of B sub S0 mesons, potentially signaling the existence of new physical phenomena beyond the standard model of particle physics. The observed level of charge parity violation exceeds what the standard model predicts for these particular decay processes, suggesting that additional sources of asymmetry operate at the fundamental level of reality. This finding provides the first direct evidence that multiple mechanisms contribute to matter-antimatter asymmetry in the universe, challenging the assumption that a single process accounts for the cosmic imbalance. The discovery implies that the physics responsible for the universe's existence may be more complex and multifaceted than previously understood, potentially involving exotic particles or interactions that remain undiscovered. The results have prompted theoretical physicists to develop new models incorporating additional sources of symmetry violation, including supersymmetric theories that predict the existence of heavy partner particles for every known fundamental particle. Alternative explanations invoke extra dimensions of spacetime or composite models where quarks and leptons emerge from more fundamental constituents. Each theoretical framework makes specific predictions about additional asymmetries that should be observable in related particle processes. The discovery has also intensified experimental efforts to search for similar asymmetries in other particle systems, including neutral kaons, d-mesons, and potentially even neutrinos. The identification of consistent patterns of asymmetry across multiple particle species would provide powerful constraints on theoretical models and guide the development of more comprehensive theories of fundamental physics. The broader significance of this breakthrough lies in its demonstration that the universe continues to reveal new secrets about its fundamental nature, even after decades of intensive study. The matter-antimatter asymmetry that allows our existence may result from a complex interplay of multiple physical processes, each contributing to the delicate balance that prevents cosmic annihilation and enables the formation of complex structures throughout the observable universe. The Standard Model of particle physics represents humanity's most successful theoretical framework for understanding the fundamental constituents of reality. This mathematical architecture describes 17 fundamental particles and 3 of the 4 known forces, predicting experimental outcomes with extraordinary precision. Yet when confronted with the matter-antimatter asymmetry that defines our universe's existence, the Standard Model reveals a critical inadequacy. The framework that so elegantly explains particle interactions and force carriers cannot account for the cosmic imbalance that allowed matter to survive the primordial annihilation. This limitation signals a profound truth. The Standard Model, despite its remarkable achievements, represents an incomplete description of nature. The universe operates according to physical principles that extend beyond our current theoretical boundaries, suggesting the existence of new particles, forces, or fundamental symmetries that governed the cosmos during its earliest moments. The quest to identify these hidden mechanisms has launched theoretical physics into uncharted territory where mathematics pushes against the limits of human imagination. Supersymmetry emerges as one of the most compelling theoretical extensions to the Standard Model, proposing a fundamental symmetry between matter particles and force-carrying particles. This framework predicts the existence of an entire shadow spectrum of particles, each corresponding to a known particle but possessing different quantum properties. For every electron, supersymmetry predicts a selectron. For every photon, a photino. For every quark, a squark. These superpartners, if they exist, would have participated in the universe's earliest moments, potentially creating the conditions necessary for matter-antimatter asymmetry. The mathematical elegance of supersymmetry extends beyond particle prediction. This theoretical framework naturally addresses several fundamental problems that plague the Standard Model, including the hierarchy problem that questions why gravity appears so much weaker than other forces. Supersymmetric particles could have decayed asymmetrically in the primordial universe, preferentially producing matter over antimatter through mechanisms that remain invisible to current experimental observation. Grand unified theories represent another revolutionary approach to extending our theoretical understanding. These frameworks propose that the electromagnetic, weak nuclear and strong nuclear forces merge into a single unified force at extremely high energy scales. During the universe's first moments, when temperatures exceeded those achievable in any terrestrial experiment, this unified force would have governed all particle interactions. The subsequent breaking of this symmetry as the universe cooled could have introduced the subtle asymmetries necessary for matter's survival. String theory pushes theoretical speculation even further, proposing that all fundamental particles represent different vibrational modes of one-dimensional strings existing in multiple spatial dimensions. This framework suggests that our observable three-dimensional space represents only a subset of a higher dimensional reality, where additional spatial dimensions remain compactified at scales smaller than current experimental resolution. The physics operating in these extra dimensions could harbor the mechanisms responsible for generating matter-antimatter asymmetry through processes entirely foreign to our three-dimensional experience. Extra-dimensional theories propose that gravity, unlike other fundamental forces, propagates through all spatial dimensions, while electromagnetic and nuclear forces remain confined to our three-dimensional space. This asymmetry could explain gravity's apparent weakness, while suggesting that high-energy processes in the early universe involved particle interactions across multiple dimensions. Such interactions could have produced preferential matter creation through mechanisms that become invisible once the universe expanded and cooled sufficiently to suppress extra-dimensional effects. The Large Hadron Collider currently represents the pinnacle of human technological achievement in particle physics, but its capabilities pale in comparison to the energies present during the universe's first microseconds. The planned high-luminosity LHC upgrade will increase collision rates by a factor of 10, allowing researchers to study rare particle interactions with unprecedented statistical precision. This enhanced sensitivity may reveal subtle asymmetries in particle decay processes that could illuminate the mechanisms behind cosmic matter dominance. The proposed future circular collider represents the next generational leap in particle acceleration technology. This facility would construct a 100-kilometer circumference tunnel beneath the European countryside, accelerating particles to energies 7 times greater than the current LHC maximum. Such energies would recreate conditions that existed mere moments after the Big Bang, potentially producing the exotic particles and interactions responsible for our universe's matter-antimatter asymmetry. Gravitational wave detection has opened an entirely new observational window into the early universe. The Laser Interferometer Gravitational Wave Observatory and its European counterpart Virgo have demonstrated humanity's ability to detect space-time distortions from cosmic events billions of years in the past. Future gravitational wave observatories, including space-based detectors like the planned Laser Interferometer Space Antenna, may detect gravitational signatures from phase transitions in the primordial universe that created matter-antimatter asymmetry. Cosmic microwave background radiation studies continue revealing increasingly detailed information about the universe's first few 100,000 years. The Planck satellite has mapped temperature fluctuations in this ancient light with extraordinary precision, revealing patterns that encode information about the fundamental parameters governing cosmic evolution. Future missions may detect polarization signatures or spectral distortions that preserve evidence of the asymmetric processes that occurred during the universe's first moments. Neutrino physics experiments represent another frontier in understanding matter-antimatter asymmetry. These nearly massless particles rarely interact with ordinary matter, allowing them to preserve information about conditions in the early universe that would be obscured by other forms of radiation. Long baseline neutrino experiments, such as the Deep Underground Neutrino Experiment currently under construction, will study whether neutrinos and antineutrinos oscillate between different types at different rates, potentially revealing the asymmetric processes that shaped cosmic evolution. Dark matter detection experiments may unexpectedly illuminate the matter-antimatter puzzle. These investigations seek to identify the invisible substance that comprises approximately 27% of the universe's total mass-energy density. If dark matter consists of supersymmetric particles or other exotic matter forms, their discovery could validate theoretical frameworks that naturally explain cosmic matter-antimatter asymmetry through the same mechanisms that produce dark matter abundance. The convergence of these experimental approaches creates an unprecedented opportunity to probe the fundamental nature of reality. Each investigation attacks the matter-antimatter mystery from a different angle, whether through direct particle creation at high energies, astronomical observation of ancient light, or detection of exotic particles that pervade the contemporary universe. The synthesis of results from these diverse methodologies may finally reveal why the cosmos chose existence over annihilation during its first moments, answering one of the most profound questions in all of science. The resolution of the matter-antimatter asymmetry represents far more than solving an isolated puzzle in particle physics. This fundamental question touches the core of our existence and challenges our understanding of reality itself. The implications extend across multiple domains of human knowledge, from theoretical physics to philosophy, fundamentally altering how we perceive our place in the cosmos. The matter-antimatter asymmetry problem serves as a critical nexus connecting particle physics and cosmology in unprecedented ways. Resolving this mystery would establish a unified framework explaining how microscopic quantum processes during the universe's first moments determined the large-scale structure we observe today. This connection between the infinitesimally small and the cosmically vast represents one of the most profound relationships in modern science. The solution to this asymmetry puzzle holds the potential to revolutionize our understanding of fundamental physics by bridging gaps between seemingly disparate phenomena. Current research suggests that the same mechanisms responsible for the matter dominance may also explain the nature of dark matter, which comprises approximately 27% of the universe's total mass energy content. Dark matter particles, if they exist, may represent remnants of the same primordial processes that created the matter-antimatter imbalance. Furthermore, understanding how this asymmetry emerged could illuminate the unification of fundamental forces. The electromagnetic weak nuclear and strong nuclear forces appear distinct at low energies, yet theoretical models predict they merge into a single unified force at the extreme energies present during the universe's first instance. The conditions that produced matter dominance may have operated precisely during this epoch of force unification, providing experimental evidence for grand unified theories that remain largely speculative. The implications extend beyond particle physics into our understanding of cosmic evolution. The formation of the first stars required sufficient matter density to overcome the expansion of space itself. Without the matter-antimatter asymmetry, no gravitational collapse could have occurred, preventing the nuclear fusion processes that created elements heavier than hydrogen and helium. The existence of carbon, oxygen, nitrogen, and other elements essential for biological complexity depends entirely upon this primordial imbalance. Solving this mystery would also address fundamental questions about the stability and longevity of our universe. Current models suggest that protons, the building blocks of atomic nuclei, may eventually decay over timescales exceeding 10 to the 34 years. Understanding the processes that created matter dominance could reveal whether this decay represents an inevitable fate or whether unknown conservation laws might preserve matter indefinitely. The matter-antimatter asymmetry forces us to confront one of philosophy's most ancient questions. Why does anything exist rather than nothing? This inquiry transcends scientific methodology and enters the realm of metaphysical speculation, yet the physical evidence demands engagement with these fundamental concepts. The Anthropic principle emerges as a natural framework for interpreting the asymmetry's significance. This principle suggests that the universe's fundamental properties appear fine-tuned to permit the existence of observers capable of contemplating these very properties. The matter-antimatter asymmetry represents perhaps the most striking example of this apparent fine-tuning. Had the imbalance been even slightly smaller, insufficient matter would have remained to form stars and galaxies. Had it been significantly larger, the universe would have collapsed under its own gravity before stellar evolution could produce the elements necessary for complexity. This fine-tuning raises profound questions about the nature of physical laws themselves. Are the parameters governing particle physics and cosmology arbitrary constants that happen to take values permitting our existence? Or do deeper principles constrain these values in ways we do not yet comprehend? The resolution of the matter-antimatter puzzle may provide crucial evidence for distinguishing between these possibilities. The implications extend into discussions of cosmic purpose and meaning. If the universe's capacity to generate complexity and consciousness depends upon an extraordinarily precise balance achieved during its first microseconds, this suggests either remarkable coincidence or underlying principles that favor the emergence of organized systems. Some interpretations propose that multiple universes exist with different fundamental parameters, and we observe this particular universe precisely because it permits observers to exist. The existential weight of these considerations cannot be understated. Every human thought, emotion, and creative achievement depends upon the stability of atomic nuclei forged in stellar cores billions of years ago. These nuclei exist only because a minuscule excess of matter particles survived the primordial annihilation. The poetry of Shakespeare, the mathematical insights of Einstein, and the technological achievements of civilization all trace their ultimate origin to quantum processes operating at energy scales far beyond human comprehension. The journey from the Big Bang's initial moments to contemporary particle accelerator experiments represents humanity's most ambitious attempt to understand our cosmic origins. The matter-antimatter asymmetry stands as testimony to the universe's capacity for generating profound puzzles that challenge our intellectual capabilities while simultaneously providing the framework for our existence. Modern experimental facilities have achieved unprecedented precision in measuring the properties of matter and antimatter, revealing subtle asymmetries that may hold keys to resolving this fundamental mystery. The 2020 discovery of enhanced CP violation in B meson decays at CERN's Large Hadron Collider demonstrates that nature continues to surprise us with phenomena that extend beyond our theoretical predictions. Each new measurement brings us closer to understanding the processes that shaped the primordial universe. The theoretical frameworks emerging from this research promise to transform our understanding of physical reality. Supersymmetry, extra dimensions, and grand unified theories represent attempts to construct more comprehensive descriptions of nature that naturally account for the observed asymmetry. The validation or refutation of these theories through experimental evidence will determine the direction of fundamental physics for generations to come. The collaborative nature of this scientific endeavor reflects humanity's collective commitment to understanding our place in the cosmos. Scientists from dozens of nations work together at facilities like CERN, pooling intellectual resources and technological capabilities to address questions that transcend national boundaries and cultural differences. The matter-antimatter mystery unites researchers across disciplines and continents in pursuit of knowledge that belongs to all humanity. Future experiments promise even greater sensitivity to the subtle differences between matter and antimatter behavior. Proposed facilities such as the future circular collider would probe energy scales approaching those present during the universe's first moments, potentially revealing new particles and interactions that operated exclusively in the primordial cosmos. These investigations may finally provide the missing pieces necessary to complete our understanding of cosmic evolution. The universe should not exist according to our current understanding of fundamental physics. Yet we find ourselves embedded within a cosmos of extraordinary richness and complexity. This paradox embodies the essence of scientific inquiry, the recognition that our knowledge remains incomplete and that nature continues to challenge our assumptions about reality. The matter-antimatter asymmetry serves as a constant reminder that the most profound truths often hide behind the most obvious observations. In confronting this mystery, we engage with questions that connect the smallest scales of quantum mechanics to the largest structures in the observable universe. The resolution of the matter-antimatter puzzle may ultimately reveal that existence itself represents the most remarkable phenomenon in nature, emerging from an intricate dance of particles and forces whose choreography we're only beginning to comprehend. The universe exists, and in that simple fact lies both the greatest mystery and the most profound achievement of the cosmos itself. The matter-antimatter asymmetry represents the most fundamental existential question confronting modern physics. Our 13 billion-year journey from the Big Bang's primordial inferno to the sophisticated particle accelerators of today reveals a universe that defies its own theoretical predictions. The cosmos should have annihilated itself within the first microsecond of existence, yet we inhabit a reality teeming with galaxies, stars, and the remarkable phenomenon of consciousness itself. The precision of this cosmic paradox staggers the imagination. For every billion particle pairs that underwent mutual destruction in the universe's earliest moments, precisely one additional matter particle survived. This infinitesimal imbalance of 1 part in a billion constitutes the entire foundation for everything we observe. Every atom in your body, every star burning in distant galaxies, and every complex molecule enabling biological processes exists solely because of this minute deviation from perfect symmetry. Contemporary experimental physics has achieved unprecedented precision in measuring the subtle differences between matter and antimatter behavior. The Large Hadron Collider at CERN represents humanity's most ambitious attempt to recreate the extreme conditions present during cosmic genesis. The 2020 discovery of enhanced CP violation in B meson decays demonstrates that nature continues to harbor secrets that extend beyond our current theoretical frameworks. Each measurement brings us incrementally closer to understanding the mechanisms that prevented universal annihilation. The theoretical implications extend far beyond academic curiosity. Resolving the matter-antimatter puzzle promises to unify our understanding of particle physics and cosmology, potentially revealing the fundamental principles governing cosmic evolution. The same processes that created matter dominance may explain the nature of dark matter, account for the unification of fundamental forces, and illuminate the universe's ultimate fate. These discoveries would fundamentally alter our comprehension of physical reality. The philosophical dimensions of this inquiry cannot be overstated. The Anthropic principle suggests that the universe's fundamental parameters appear precisely calibrated to permit the existence of observers capable of contemplating their own origins. The matter-antimatter asymmetry represents perhaps the most striking example of this apparent fine-tuning. Had the imbalance been marginally different, the cosmos would have remained a sterile expanse of radiation, incapable of generating the complexity necessary for stellar formation, chemical evolution, and ultimately, life itself. The collaborative nature of this scientific endeavor reflects humanity's collective determination to understand our cosmic origins. Researchers from dozens of nations contribute to experiments at facilities like CERN, pooling intellectual resources and technological capabilities to address questions that transcend national boundaries and cultural divisions. The matter-antimatter mystery unites scientists across disciplines and continents in pursuit of knowledge that belongs to all humanity. Future experimental programs promise even greater sensitivity to the subtle asymmetries that shaped primordial physics. The proposed future circular collider would probe energy scales approaching those present during the universe's first moments, potentially revealing exotic particles and interactions that operated exclusively in the cosmic dawn. Advanced astrophysical observations of the cosmic microwave background radiation may provide independent evidence for the mechanisms responsible for matter dominance. The resolution of this mystery may require revolutionary advances in theoretical physics. Supersymmetry predicts the existence of entirely new categories of particles that could have participated in creating the observed asymmetry. Grand unified theories propose that the electromagnetic weak, nuclear and strong nuclear forces merge into a single interaction at the extreme energies present during the universe's birth. Extra-dimensional models suggest that our familiar three-dimensional space represents merely a subset of a higher dimensional reality where the fundamental laws of physics operate according to principles we have yet to discover. The technological applications emerging from this research continue to transform human civilization. The World Wide Web originated from the need to share information among particle physicists at CERN. Medical imaging techniques rely on antimatter production in positron emission tomography scanners. The computational methods developed to analyze particle collision data drive advances in artificial intelligence and machine learning. The pursuit of fundamental knowledge consistently generates unexpected practical benefits that enhance human welfare. The educational impact of this research inspires new generations of scientists and engineers. Young people worldwide engage with these profound questions about cosmic origins, developing the mathematical and scientific literacy necessary to address the challenges facing human civilization. The matter-antimatter mystery serves as a gateway to understanding the interconnected nature of scientific disciplines and the importance of international cooperation in advancing human knowledge. The universe exists in apparent violation of the symmetry principles that govern fundamental physics. This single fact represents both the greatest mystery and the most remarkable achievement of the cosmos itself. The matter-antimatter asymmetry reminds us that our knowledge remains fundamentally incomplete and that nature continues to challenge our assumptions about reality. The resolution of this paradox may ultimately reveal that existence represents the most extraordinary phenomenon in the natural world, emerging from quantum processes whose complexity we are only beginning to appreciate. The journey continues. Each new experimental result and theoretical insight brings us closer to understanding why something exists rather than nothing. The universe should not exist according to our current understanding of physical law, yet we find ourselves embedded within a cosmos of extraordinary beauty and complexity. In confronting this mystery, we engage with the deepest questions about the nature of reality itself, pursuing answers that may forever change our understanding of what it means to exist in this remarkable universe that defies its own theoretical predictions.